And you can see if you press participants that the number are increasing. So,
oh, very good.
So good afternoon, everybody. Welcome to our NITheP Colloquium. We will wait a minute to give everybody the opportunity to join us online because we had lots of registrations, and I can see that slowly the number of attendees is increasing exponentially. Yeah, it's flattening now. Yeah, we're already at 70. That's very good. Let's see if we can break the 100 milestone. Okay, 78, hop, hop, 80. Okay, I think the curve is flattening, as they say these days. Yeah. Okay, maybe we waited a minute. Okay, no, there's another pickup of cases. Okay, now I think we are settling around 90 participants. That sounds very good. Okay, then let's start this colloquium officially. So good afternoon, everyone. If you are in South African time zone, if you are in some other time zone, good morning or whatever. My name is Francesco Petruccione, and as probably some of you know, since a month or so, I'm the interim director of NITEX, which is the National Institute for Theoretical and Computational Science, which is supposed to be the institute that will grow out of NITheP in the near future. I'm very happy today that we managed to initiate this new colloquium series, yeah, just to bring together all the NITheP associates and all the friends of NITheP in South Africa and abroad. And we will try to have this event at least as a bi-weekly event at the beginning, and then we will see if we have to increase the frequency depending how people react to this. Before I introduce the speakers to you, I just wanted to briefly, if you're not expert webinars participants, explain to you the rules. Only the panelists, the people you see, are allowed to speak, but you will be able to interact with them through the question and answer facility in Zoom, which you find on the bottom bar, just one left of the three dots, the Q&A. So if you press the Q&A, a little window pops up, and there you are most and welcome to pose your questions, and and our two speakers will answer them at the end of their presentation. Yeah. So let me introduce now the speakers. We have two speakers today. You know, I forget always what I want to say. And I'm really happy that we can welcome them today. Wilfred Ndifon, that most of you might not know because he's a theoretical biologist and our audience is typically made up of physicists, but hopefully that will change. Yeah. And Neil Turok, who most of you know. Yeah. And when a few weeks ago I asked Neil if he wanted to be our first speaker, I was sort of thinking that he might tell us that he will speak about some recent cosmological topic or, or something more fundamental. Yeah? And I was absolutely pleased that he chose a topic that is close to all of us these days, because learning about methods to screen better viruses is something that all of us are interested today. And I'm particularly pleased for it because, you know, since NITheP is in a transition to NITEX, yeah, topics like this will become more and more relevant for the institute. So I'm absolutely 100% happy that we start with a bang, not a big bang, but a biological bang. Yeah, and so thank you very much to both of you. So let me start by introducing Wilfred. That Wilfred was born in Cameroon, but he concluded his studies with his PhD in Princeton, and he's now professor of theoretical biology at Ames in Rwanda. Yeah? Neil Turok, as all of you know, was born in South Africa. He's the founder of the African Institute of Mathematical Sciences with the first kind of site in just outside Cape Town. And, and as I mentioned before, he's more famous for testing theories of the universe than for testing for viruses, but nevertheless, yeah. He was a professor of physics in Princeton, in Cambridge. He was for many years director of the Perimeter Institute. And in a few months, he will take up the Higgs Chair for Theoretical Physics at the University of Edinburgh. Yeah? So we are very, very happy for both of you to be here with us today and to listen to your talk on how to find, not how to find, you found it, on a better strategy to find people infected with COVID-19. And according to plan, I think Wilfred will speak first and will follow up by Neil. So Wilfred, over to you. You're welcome to share your screen
now. Thanks everyone for joining us for this brief colloquium. Neil and I will take turns presenting. I will discuss the background to our work. Neil will provide details of what we did, and then I'm going to summarize and talk about some applications. Many of you are by now, I believe, familiar with this timeline of some important events that have happened during the last several months. In December, there were reports of clusters of pneumonia cases in Wuhan, in China. The disease was later found to be caused by a variant of the SARS coronaviruses, and it was named COVID-19, which is now a famous name. In January, COVID-19 was reported in Thailand. At the end of that month, the WHO declared COVID-19 a public health emergency of international concern. In March, the WHO declared COVID-19 a pandemic. And as of this morning, according to the Worldometer's website, there are 3.6 million people who've been infected and about 250,000 deaths. Now, COVID-19 is not the first pandemic. Many of us who study this war that's happening between pathogens and humans know that it's not going to be the last. There will be many more pandemics, some much more serious. And it is unfortunate that currently humanity is not as well prepared for this pandemic as it should be. And this is given despite the history we've had. In the 12th century, it's reported that about 90% of the population was killed by the plague. In the last century, the influenza virus pandemic of 1918 killed up to about 40 million people. So we have these pandemics that are very serious, very deadly, and we need to prepare for them. And preparation requires science. It requires scientific advances. And AIMS is making a small contribution, not just towards supporting the response to the current pandemic, but also preparing us for future pandemics. We're going to talk about a small part of the work that we're doing related to COVID-19. I live in Rwanda, and that's where the AIMS's secretariat is located. And so we've been working with the local task force that's responding to COVID-19, providing them with mathematical modeling support. This is a timeline of some key events that have happened here. So on the 3rd of March, we had our first imported case. On the 21st of March, there was a lockdown. We've been making projections that help the team to do operational planning, determine how many tests they need, how much space they need to quarantine people or to isolate those who are infected and things. Right of this slide, some projections we made on March 30th. This made a small contribution towards a decision that was taken a day later to extend the lockdown locally. we had projected up to about 250 cases by the end of last month. We did have about that number, but we expected that there would be a decline in the number of cases. That happened until about the 25th of April when we had a new source of infection. So the country was doing very well until we had people transporting food across borders, bringing in new infections. So you see a spike of cases. So as of this morning, there are 259 cases and no death.
That April should be May, right, Wilfred?
Sorry, May.
5th of May. Yeah. Thanks.
So this is a small team of AIMS working with the task force locally. There are 2 PhD students, Maurice and Eva, and a postdoc, Pacific. Now, testing is known to be a key to containing COVID-19 and to containing any infectious agent that's spreading in the population. To maintain the prevalence at a certain level, you need to know infections that come up, that emerge, are detected through testing, and the infected people are isolated, and the people they've come into contact with that could be infected are quarantined. So essentially, you need to do a lot of testing. You need to do a lot of work just to stay at a certain level of prevalence. Ideally, we would go to a very low prevalence and do all this work to maintain that low prevalence. Unfortunately, the testing that's being done around the world is not enough. South Korea is one of the success case stories. They've tested about 12,300 people per million population since the infection entered the country, and they have managed to control the infection without imposing some more stringent control measures like the lockdowns that we are familiar with. In Africa, South Africa, Ghana, and Rwanda are some of the countries that are doing better, but still the number of tests per million population, it's relatively small. And there are many reasons for this. The tests, they need expensive equipment, they need reagents that are costly and also in short supply. Most African countries are not manufacturing these reagents locally. And it also takes time, approximately 3 hours per run of this test. So these are all resources that many African countries cannot really afford. And so how do we overcome these difficulties? Are we going to talk about an approach to doing so, which is based on group testing? So more formally, we have a set of individuals we denote this set by A. There are n individuals in that set, and a subset of them, which we call K, they're infected. And we want to find K subject to certain constraints that are informed by practical considerations. We need only a few tests, and with a small amount. The longer you take to, the more the chances the disease has to spread in the population. So denote by small k the number of infected individuals, which is typically much smaller than the number of individuals we're interested in studying. T would be the number of tests you need to identify the infected individuals. Now, in the approach of group testing, we pool these individuals. We group them and then combine the samples from these individuals and test once. So we're going to denote we're going to arrange these pools in a matrix, which we'll denote by X, just to facilitate the discussion. This is an example of a test matrix. You have along the columns, individuals, along the rows, different tests that are done. You have a 1 in a particular position if the corresponding individual is present, if the sample from that individual is present in the test indicated by that row. So the outcomes are typically in the form of a vector, which takes whose entries are either 0 or 1. So the test is either positive or negative. So what we want to do is to have a series of these testing matrices, the designs, and find a function that takes these matrices as an input together with the output vector, and then produces as output some subset of A, which hopefully is exactly the same as the subset of interest. And so you see that there are a series of test designs, and each one is obtained represents a particular round of the testing. So if you test R times, you get R of these test designs, and you pass this into your function, which then tries to determine K. Here are some characteristics of the algorithms that exist. There are those that require only one round, so they are non-adaptive. Typically, the first step is to check whether there's no infected person. So you pull everybody and then you test. If the test is negative, you stop, nothing to do, you don't have anything to do. If it's positive, then you have to enter the key steps of the algorithm. And the non-adaptive algorithm do only one such test. The adaptive algorithms typically do more than one. Now, the outcomes that are used, inputs into this algorithm, they can be either noisy or noiseless, right? So the outcome can be determined in a precise way with no error, or there might be some errors. So you have false positives and false negatives. Typically, the non-adaptive algorithms, they're not guaranteed to find the set of infected individuals. But they can find some set, which is called a satisfying set, such that every positive test an individual from that satisfying set. And there's no test that has an individual from that set that's negative. Now, I'll go through an example of one of these algorithms, an adaptive algorithm called the binary splitting algorithm, one of the earliest such algorithms to be developed. It's very simple. You just take your n individuals, you test all of them. If your test is negative, you don't have anything to do. If it's positive, then you divide into approximately two subsets of approximately equal size. You take one of these subsets, you pull all the individuals and test. If the test is positive, then you set your set of interest to be that subset that's positive. If it's negative, then you set your set of interest to be the complement of the complement in A of that negative set. And so with this algorithm, in each round, you're splitting your set into approximately two parts. So essentially, you're going to find an infected individual after at most log to the base 2 of n tests, where n is the number of individuals you started with. So this algorithm, if you have k infected people, you can identify them after at most, about k log 2n plus an order k term. The proof of this statement is given here, which is straightforward. I'm not going to spend time going into it. I'm going to talk about a variant of this algorithm developed by Huang in 1972. And its idea was try to reduce a divide in the set. The subsets are exactly of a size that is a multiple of 2, right, or a power of 2. And so, another made was that in each round, individuals that are found to be negative, they're eliminated. So you don't have to consider continue including these individuals in the test. And this is one of the best, the most efficient algorithms known. It's near optimal. We're going to talk later about an information theoretic bound for the performance of these kinds of tests. And you see that this algorithm gets close to that bound. Now, some performance characteristics of these algorithms. I'm going to look at, we're going to look at 4 parameters: the number of tests that are done typically. So the non-adaptive tests will do a number of tests that is larger than the smallest predicted by information theory. There was an algorithm published in 1943 by Dorfman, which was the pioneering algorithm in this area, in this field. And that algorithm takes about 2 square root of kn tests to find the k infected individuals. The algorithm I just mentioned takes approximately, when n is much larger than k, approximately the information theoretic bound, which is given there. Now, how long do the tests take? Well, if you take tau to be the amount of time that a particular run of the diagnostic test lasts, then the non-adaptive algorithm would essentially, since they are run in parallel, will take tau hours, for example. Dorfman's algorithm will take 2 tau hours because it's done in 2 steps. Wang's algorithm will take a relatively large number of times of hours, depending on the value of n. These algorithms use the samples a certain number of times, and in the adaptive algorithm by Wang actually uses the sample many more times. And this has some disadvantages, because each time you're removing a small sample from a given sample, the measurement you make is not error-free, right? So you're making some error each time you do this. So the fewer number of times you use a sample, the better. And as I mentioned earlier, the non-adaptive tests generally don't give you a guarantee that they would find the K, the set of infected individuals you're interested in. They will give you an approximation of that set. The adaptive algorithms tend to give you the set of infected individuals. Now, so this is just to give you an idea about what we've done. So we have an approach that describes the problem a bit differently. In particular, our outcomes are actually matrices, they're not vectors. So there's more information that you can learn from these outcomes that in the case when k is equal to 1, allows you to identify the infected individual without error, assuming the test itself is done without error. And there are a number of algorithms that work on these test matrices and output vectors, and they try to decode these inputs to give you an approximation of k. When k equals greater than 1, you can apply the same or similar algorithms to our own setup. But you can also identify k exactly, but this time you have to do the test, in essence, in an adaptive way, iteratively. You do many more, you run our algorithm more times. And Neil will give you more details about that. I will now pass the hand over to Neil.
Francesco on...
Neil, you are...
Are you hearing me?
Yes, yes.
Okay. Actually, I just want to go to my own screen. Wilfred, you need to switch off your sharing. Yeah, okay. So now hopefully mine will work. Okay, so yes, so I just wanted to begin by congratulating Francesco on taking over NITheP, and obviously this colloquium is the first of many things he's going to do, and I think we're all very excited to see what he will do with NITheP. Secondly, I just want to say that, can you hear me okay?
Yes, yes, we can hear you perfectly.
All right, excellent. Secondly, I wanted to just say what a privilege it's been to join Wilfred and his team. They're really doing pioneering research in Rwanda, which is a pioneering country in the manner in which it's adopted science as a cornerstone of its policies. And so, yeah, it was really wonderful when few weeks ago, Wilfred wrote to me and said, you know, we're looking at these pool testing approaches, and do you have any good ideas about how we can improve things? So it's been very exciting to join in this effort. And I think the real excitement won't be my talk, but I encourage you to wait for the end, because Wilfred is going to show you some real data and real field trials which are happening of this mathematics. And of course, that is really when things get exciting. So just to recap what Wilfred told you, let me do full screen. The basic idea Dorfman had in 1943 was to do with the concept of group testing. So you've got some population of size n, and some of them may be infected. And one approach to testing them is to test them one by one. That's obviously, you have to use n tests, and that's not very efficient. For example, and Wilfred already gave the example, imagine that 0 were infected, and imagine that you could pool all the samples from the whole population, and in one test, you would learn they're all negative. Well, then you only need one test. So these are the two extremes. And Dorfman asked himself, in any given situation, what is the optimal group size to test? So he took a population of size n, he broke it up into k groups of size n over k each. So I've divided this group of 18, the population of 18, into groups of size 3. And then he imagine testing the groups together. And so you just have to do 6 tests. You find one of the groups is positive, that's the red group, but you don't know which individual in that group is positive. So his procedure was then to test every single member of that positive group. And in this case, there's one positive individual. So he had to do 6 tests to find whether each group is positive or negative. And then he had to do 3 tests on the positive group. So 9 in all, but that's a lot better than 18. So if you consider it more generally, the number of tests you need is k, because you have to test each group, plus n over k, because that's the number in each group. And so that's the total number of tests. That is to find one infected individual. So that's when you assume there is only one, then that one individual lives in one of the k groups, and to find it, you will need k plus n over k tests. Now that function, k plus n over k, is graphed, and obviously if k goes to 0, you're now in the regime where you essentially have to do n tests. If k gets very large, then the number of tests is growing with k, linearly with k. So there is a minimum, and it's easy to find the minimum. Just differentiate with respect to k and set the answer to 0. And the minimum is where k is root n, and the number of tests is twice square root of n. And that's obviously much less than n, if n is a large number. So there's a big gain in testing in groups. Now, more realistically, you don't know that there's one person infected. More realistically, you may only know the probability or an estimate of the probability that any given person is positive. And that's called the prevalence. So again, Dorfman took his population, divided it into k groups of size n over k. In this case, there are 2 positive groups and 2 positive individuals, but his procedure was the same. But now you have to compute the outcomes using probability. The probability a group is negative is 1 minus p, that's the probability an individual is negative, to the power n over k. And the probability a group is positive is just 1 minus the probability that it's negative. So now he works out the expected number of tests per person, t over n. Just as before, we have to do k tests on all the groups. then the number of groups which will be positive are P prime, the probability a group is positive, times K. And so that's the number of positive groups. The expected number of positive groups is P prime K. And each group has N over K members, so you have to do N over K tests. So when you work that out, you just get K over N plus P prime as the answer. And if you go and look at the formula for P prime in the limit of small k compared to N, it's just P N over K. So once again, we find a function which diverges at large K, like K. It diverges at small k, like 1 over K. It has a minimum, and the minimum is where the group size is 1 over square root of P. And the number of tests per person is 2 square root P. So that was Dorfman's proposal for group testing in 1943. Now, the proposal which we came up with recently is quite different. And essentially, it's based on the observation that Dorfman's procedure is one-dimensional. You essentially put everybody in a line, and you chop up the line into pieces, and you test the pieces. Well, what if you didn't do that? What if you arranged everybody as points in a cubic lattice in some arbitrary number of dimensions, let's say D dimensions? And so the total population would be the size of your cube in D dimensions raised to the power D. Now, what's the process? Well, just like with Dorfman, you slice up the population, or the N, in but now you may slice it in each of the D directions. And so we leave D and L as free variables. Of course, they're constrained so that N is L to the D. And we try to ask, what is the optimum L and the optimum D? So let's first of all consider this to be a cube. So all lengths L are equal. That's the simplest case. And then the number of tests to find one infected individual is just D, the number of different slicings, one for each direction in higher dimensional space, times N to the 1 over D, which is just L from the formula on the left. L is N to the 1 over D. So DL is the total number of tests. If you do these slicings in each of the D directions, and if there's only one individual, then every slicing will uniquely identify the coordinate of that individual in this D-dimensional space, and your testing is finished. So that's the number of tests. Now D is a free parameter, so you can minimize the number of tests with respect to D. The minimum you find is D is log N, where N is the size of the population, and L is E, the Euler's number, 2.718. But of course, in reality, L should be an integer, and the closest integer to E is 3. And so the optimum hypercube you can use has a side 3. And the minimum number of tests you need is 3 log base 3 of N. Now you may say, you know, what happened to 2 and 4? Why are they not so good? And the answer is very simple, that 2 over log 2 and 4 over log 4 are equal to 2.89, whereas 3 over log 3 is 2.73. It's a minimum in the out of n over log n, where n is an integer. And that's how 3 comes out. Of course, E over log E is just E, so that's, which is 2.718, but that's quite close to 3 over log 3. The number of tests you need is only log, depends on the logarithm of n. Sorry, it's n log n, and much less than Dorfman, 2 times square root of n. So let's now ask, why is this cube symmetrical? You know, And what we can easily do is take all the sides of the cube to be different lengths, L1, L2, L3, then the volume is just N, is the product of all the L's, and the number of tests you need to find the individual is the sum of all the L's. And then we have to put in a constraint, which we could do with a Lagrange multiplier, that N is the product of all the L's. Now, differentiating with respect to the L's and setting all those to 0, you find all the L's are equal. So a symmetrical hypercube is preferred, whereas Dorfman used one which has essentially one of the lengths equal to N and all the others equal to 1. So the reason this hypercube does better is because minimization problems generally favor symmetry. So let's imagine we had 2 infected individuals, and they're located at these 2 points of the hypercube. Well, the slicing in the X direction would capture those 2 points on different slices. But the slicing in the Y or the Z directions would capture them on the same slice, so that would be degenerate, and you could not uniquely identify their coordinates. However, if these points happen to be arranged in this way, then the configuration is non-degenerate, and every slicing finds the unique value of the coordinate. It's not hard to work out that a non-degenerate configuration has probability 2/3. Basically, the first point has to go on 1 of 3 slices, and the second point can now go in any 2 of the other slices, and therefore there's probability 2/3 that it is not degenerate and unique. If we have 3, the only way you get non-degenerate is in a configuration like this, where the points are not on the same slices in each of the 3 directions. But it's easy to work out. This occurs with probability 2/9. So if you slice up your population on all possible slices, and if N and D are large, there will always be many slices which are non-degenerate. And those are the slices you use for the algorithm to work. So there are small issues with the non-degeneracy. And in this sense, when you get up to 3 and higher individuals, our algorithm becomes adaptive and not parallel. Now we repeat what Dorfman did. Take a group of size n. Instead, we're going to assume Poisson statistics with the mean lambda equal to p times n. So that's the mean number of infected individuals. So it could be, the actual number could be 0, 1, 2, 3, or more. The probability that m individuals are infected in your population of size n is this formula, e to the minus lambda, lambda to the m over m factorial. And now you can compute the expected number of tests per person. It's given by this formula. If there's no individuals, that's the first term in the equation, that's the 1. So you only need 1 test. If there are more than one, if there's 1 or more infected individuals, you need R sub m tests. So in particular, if m is 1, 2, or 3, you only need 3. You need 1, 2, or 3 tests. If m is 4 or above, it turns out you need slightly more than m, 4 1/3 or 5 1/fraction, or 6 1/fraction tests. So it's a very good approximation to treat the number of tests needed, the Rm as m. You can now do the sum exactly, and you find the second displayed formula, where the first term again comes from 0 infected individuals, and the second term comes from the combination of all higher numbers of infected individuals. Just like Dorfman, you can minimize this function. So what we're doing is we're keeping the prevalence p fixed, but we're adjusting the size n of our population to minimize the cost per person. And this function has a minimum at lambda 0.35. That's telling you that the optimal size of the group you took, size of the group is 0.35 over P, over the prevalence. And more intuitively, what that's telling you is you choose your group size so that the probability of getting no infected individuals is 70%. Most of the time, you're getting this tremendously efficient test where I just do one and everybody is clear. The probability of getting one person is 25%, 2 people is 4%, 3 infected individuals is 1%, and basically you've covered all the possibilities. The probability of more than 3 being infected is very small, and those are the cases which are trickier to deal with in this Hypercube approach, but you don't often encounter them. So the number of tests per person is EP log 1 over P, very much better than Dorfman, which is 2 root P. And this number of tests seems to be roughly, seems to be consistent with the fastest algorithms known in computer science currently, which Wilfred described as error-free and non-adaptive. So here's some specific numbers. If we take a prevalence in the range 2% down, 2.3% down to 0.78%. And by the way, the typical expectation for prevalences now is about 2%, though they're really huge uncertainties. Nobody really knows. The 2% comes from a study in Iceland, which seems to be one of the few really careful controlled studies, including people who don't have symptoms, trying to understand what fraction of the population had coronavirus at the time of testing. So that number is quite uncertain. But if the prevalence is around 1%, the optimal group size is 27, and the reduction in cost, in other words, the factor by which the number of tests is reduced, is between 4 and 10. If the prevalence gets lower, between 0.26 and 0.78%, the group size is 81. You have to test 81. You have to you construct a hypercube in 4 dimensions and slice it in 4 different ways. And then you can reduce the cost between 10 and 24 times. If the prevalence gets as low as 0.09 or 0.03%, which of course has to be the objective, now the group size becomes large, almost 1,000, and you start getting cost reductions of a factor of 100. And you're now working in a space of high dimensions, 6 dimensions. Very roughly, as the prevalence falls by a factor of 3, you increase the group size by a factor of 3, and you lower the cost by a factor of 3. So clearly, there's a huge incentive for governments to spend money now to lower the prevalence, because that is going to lower the cost of testing. And if we can keep the prevalence to a very low level, then we can test everyone every week for a completely affordable cost. So Wilfred also mentioned this information theory bound. I won't go through it in detail. You can read the slides later. But essentially, if you just state the problem as finding k infected individuals among n, in a group of size n, then there is a lower bound on the number of tests, which is basically saying you compute the entropy in this unknown distribution. You know that you only gain information in bits in this test. So the information is the number of tests times log 2. And you have to get at least as much information as the entropy in the unknown distribution in order to learn all the details of the unknown distribution. And so from that, you get a lower bound. It turns out this lower bound is p log 2 1 over p, whereas ours was p log 1 over p, log e, natural log of 1 over p. So our Hypercube search requires e log 2, which is a factor of 1.88 more tests. But the only known algorithms which achieve this bound from information theory or come close to it, no algorithm achieves that bound, but the binary searches come close to it. Those algorithms are serial, as Wilfred indicated. You have to repeat many, many times. And that takes time, which you cannot afford. Whereas this Hypercube algorithm has the advantage that most of the time, when you're just finding one infected individual, it's completely parallel and very fast. So the problem with taking time in testing is that the individuals who you've got samples from, but you're spending all this time testing the sample, those individuals are still spreading the disease because you don't know who they are. So they are still at large, interacting with other people. A study in China of the spread of the disease from Wuhan showed that the doubling time for the infection was approximately 2.4 days. So this binary search, if every step occupies several hours, as a PCT test does, then typically you wouldn't expect to do more than 3 of those per day. And the problem is that if you need many more than 3 tests, you're going to take several days to identify the infected individual. And during that time, you're spreading the disease. So the efficiency gain of 1.88 by the binary searches is outweighed by the doubling or exponential growth of the prevalence during the testing time. And that formula is 1 over p to the tau over tau 2. So if each test takes a third of the day, let's say, and if the prevalence is less than 1%, the Hypercube approach is preferred. The advantage of a binary search gets lost at low p. So finally, let's just think about Rwanda and the cost of testing. So the GDP per capita in Rwanda is very low. It's a largely rural country. GDP per capita is about $900 currently. That's $18 per week. Per person. Clearly, if every coronavirus test costs between $30 and $50, Rwanda cannot afford to test everyone every week. It's simply impossible. But if we can, through initially investing in testing, tracking, tracing, and isolating, and if through that the prevalence can be brought below 0.1%, and if we can combine, we will need to combine 243 samples in a test, the cost could fall to 30 cents by a factor of 100. An efficiency gain of 100 is possible. Now each test is 30 cents to 50 cents. Now if you test everyone every week, that is just about affordable. Similar statement could be made for South Africa. South African GDP per capita is about 7 times Rwanda. So this is certainly affordable. It would be hard to afford it with one-by-one testing, because that would take about $2,500 per person per week. Per person per year. It would take $2,500, which not really affordable for South Africa, but if you can reduce it by a factor of 100, then it's certainly affordable. So the great thing about this method is that the cost per person falls very quickly as the prevalence in the population decreases. So there's a huge incentive for decision makers to invest now, reduce the prevalence, and lower the cost of searching for the disease. So I'm going to hand back to Wilfred for the most exciting news, which is the actual implementation of these ideas.
Yeah, thank you, Neil. And I think we need to unmute. Wilfred, I think you need to unmute your microphone. I'm trying to do it here, but it doesn't work. Yeah, perfect.
Hear me?
Yes, please, go ahead, Wilfred. Thank you.
So now, if you have pooling, the things you need to check, positive sample, other samples, when you pool each positive samples, you dilute order of the total number of samples. So we did this experiment, and we demonstrated that you can dilute a positive sample by a large factor, up to 100, and you still get a positive test. So on the left-hand side of this slide, you see curves, fluorescence curves obtained from this this machine that is the standard on which the standard diagnostic test for COVID-19 is built. And each on the x-axis you have the cycle. So what the test does is it amplifies the genetic material that you start with in cycles. So if the amplification is perfect, after each cycle, then amount of the target material doubles. Typically, it's slightly less than a two-fold increase. So if you amplify up to about 40 times and you don't find a sharp increase in the signal from the target material, then you conclude that the material is not present. So the signal needs to increase above a certain threshold. Typically, when you have the material present, you see the signal above threshold signal after about 30 cycles of amplification. So here we took two samples, diluted them in ratios in different ratios, and tested each, and we showed that you could in fact detect the positive samples in this larger pool. Now, once we've done that, we did the team, we went to the field, the community to do testing, okay? And we could use the algorithm to tell them how to group the samples that they obtained. So for example, based on preliminary data we had, mostly obtained from screening people at some risk of infection, we had estimated an upper bound for the prevalence of the disease in the community to be about 2%. So our algorithm tells us that the pool should be about 17.5. For simplicity, we used 20. So this makes the work of the experiment that is easier. We had samples from 1,280 individuals, so there were 64 pools. We tested all of them, and we found that they were all negative. So this represents a 20-fold gain in efficiency. Instead of a 1,280 tests, we did just 64. And also from this data, we got a better estimate of the prevalence. So when next we go to we have the efficiency gain will be much more than 20, because we can design the sample sizes in a way that reflects better the actual prevalence of the infection. So on the right-hand side, you see the results of the tests from this 164 samples. And you see the curves, there are some controls. So the test amplifies certain genes that we know are found in the virus. And there are some curves that come from the amplification of those genes and restricted behavior. But for all the 64 samples, the amplification doesn't generate cells that exceed the threshold of interest. So essentially, all those 64 samples are negative. So this represents an important contribution to the team and to the country. And as Neil mentioned, we're really appreciative to the team for being open to the ideas that we providing to them. And this collaboration is really allowing the country to do a lot more tests. Now we're scaling up testing, and with this algorithm, that will become possible. It will become much more cost effective to do that, because the lockdown has been partially lifted, and testing has to be scaled up to ensure, as I said earlier, that we quickly identify and isolate any infected individuals. So in conclusion, we described the new approach to parallel non-adaptive testing for identifying people who are infected within the population. It cuts down the testing costs because it reduces the number of tests you have to do relative to what would naively be expected. That of the best non-adaptive tests. It also reduces time much more than do the tests that approach the information theoretic bound, which are adaptive in nature. And this approach is preferred to the near optimal adaptive testing approach, particularly when the prevalence is small. And we are, as I mentioned just now, we're already using this in Rwanda to do COVID-19 surveillance, identify hotspots, so that public health officials can respond more quickly. So I want to thank first Francesco for giving us this opportunity. And I'm hoping this to be the start of a collaboration with AIMS. We have a center in South Africa, which I am using as my background, the image of which I'm using here. And we're doing many similar things. And in fact, I think of theoretical physics, all science that searches for some general principles that in nature is theoretical physics in my definition. And so we are doing a lot of that at AIMS, and I think there will be many opportunities for collaboration with NITheP. I want to thank the government of Rwanda, and especially the people who are working in the task force, for the collaboration, the openness that they have displayed, particularly Leon Mutesa and Sabine Nsanzimana, and also the funders of AIMS. Thanks.
Yeah, thank you very much, Wilfred, and thank you very much, Neil, for your wonderful talk. I think some of our participants have posted some questions in the Q&A. I don't know if you would like to answer them. Yeah, thank you.
So I'll start with, I look briefly at two questions that were posed by an AIMS alumna. Okay. So they are very intelligent questions posed by somebody who went through AIMS. So the questions are from Tendai. One, so Tendai is asking, if you're pulling samples, then you need a test that's highly sensitive. And I think I partly answered, we've partly answered that by showing that you can actually dilute samples by up to 100-fold, and you're still able to determine whether they're positive. Now, one of the reasons for the relatively low sensitivity of the tests for COVID-19 is the fact that you have variable amounts of virus in the samples that are collected from individuals. In fact, soon after you're infected, if you're tested, you're unlikely to test positive because those experiments have shown that the virus reaches levels that you can then detect using the standard tests. And so one way to counter this is to do serial tests. So you test at different points, you wait for the course of the infection to reach a point where the virus is, and this is being done when people are quarantined, they are tested at different time points. And as you can imagine, parallel approaches to identify infected people, like what we've described, would make this process much more cost effective. Now, what this low sensitivity does in mathematically, it decreases the effective prevalence. Basically, some people who are positive, you think they are negative. And so it decreases the effective value of P. That's how it enters into the analysis. The false positives are actually rare with this standard test. So Tendai, I hope I've answered your questions.
Yeah, maybe let me also answer one of Tendai's questions. She asked, are you talking about pooling samples into one batch and then testing that? And indeed, that's exactly what we're talking about. So if you picture the population as this cube in d-dimensional space, we divide it into 3 subsets. And then what you have to do is take all this, you have to take subsamples from everybody in one of those 3 subsets and join them all together and test that. So a major constraint is indeed the volume of the testing, the capacity of the test equipment for a certain amount of volume, because you don't want to dilute the sample too much. You want to make sure there's at least roughly 10 viral particles in the testing volume. So if you can make the testing volume larger than current machines, you would be able to pool a larger number of samples and increase the efficiency. So we are thinking about talking to engineers who design these machines. There are many new designs being thought of, and this consideration should come in, that the machines should accommodate a larger sample than current ones do in order to allow this for accurate testing, for many samples to be pulled together without reducing the number of viral particles in the test volume too much.
Thank you, Neil. And
if you look in the paper, we give some more details about this, some more experimental details, and indeed these are the biggest constraint on this method currently. So Wilfred and his team's demonstration that you could actually test 100 samples together and still detect only 1 positive, that's really state of the art in the field.
Thank you, Neil, for that. Somebody asked the question whether we are using the Hypercube method in South Africa already, and probably the answer is no. But the hope is that we will start tomorrow.
Yes, exactly. No, the general rule is that mathematics can be of great assistance in this type of screening. And we're not sure our algorithm is the most optimal. For example, it's not obvious that a hypercube is the best geometry to use. Maybe there are other geometries which are even more efficient. It's very, very nice for mathematicians or physicists to discover that the kinds of things they normally think about can be very useful in such an applied situation.
Yeah, thank you very much. Then I'm looking at the time, and I know that all things shouldn't last more than 1 hour to be interesting. So I think it's the time has come to thank Neil and Wilfred again very much for their fascinating talk, which is really combining the theoretical with the practical in a fantastic way. And if we pull in also the engineers building better machines, that will be a full
exactly.
solution. Yeah. So I hope there were engineers watching the talk, but we will put it on YouTube and we will address them to the link. So again,
Fantastic.
thank you very much again, Neil. Thank you very much, Wilfred. Thank you very much to all the participants. And we had more than 160, so that is a very good start, I think. Yeah.
Great.
And we will hopefully soon announce the next one. Yeah. So thank you very much again to all of you. Have a good evening, and we will see you here again soon. Thank you very much.
Yeah.
Bye.
Thank
bye.
you. Thank you.
Thank you, Wilfred.
Thank you.
Thank you very much. Thank you.
Bye.
Bye.
Bye. Thank you very much. I will end the meeting now. Thank you.